All right, yeah. Thank you for the opportunity to speak here at the 25th anniversary of APART. So, yeah, I had the pleasure of being member of APART from the very beginning, and I enjoyed it very much. So, essentially, APART started when I did my master thesis, my PhD thesis, and it helped me a lot to get in contact with this network and discuss all the ideas I had with you guys. And so to some degree, what I'm showing today is also basically your contribution as a group. And so what you can see here is the Computer Science Department of Technical University of Darmstadt. So we have multiple buildings, but this is the, let's say, oldest building and the central building. All right. So I think the starting point of all our work of performance analysis was the observation that, the observation that we didn't use our machines efficiently. And the way we established this statement was we compared it always to the peak performance. So there was always the saying, applications do not even achieve 10% of peak performance. And well, while this is true, and there are also some positive exceptions, for example, on the Earth simulator, where actually codes achieved more than 50% of peak performance, it is true that in many cases, the actual performance was maybe 10% or less than 10% of peak performance or less. But so I'm not so sure whether this argument was really so sound, because so peak performance is essentially only the performance that a system is guaranteed not to exceed. So there's no reason to believe that you can actually achieve peak performance or that it is reasonable to achieve peak performance. So maybe we have tried to chase a ghost with our work, but still I think we can cite numerous examples where we actually improved performance, which is good. All right. So this is where I started. So I basically was confronted with event traces, visual trace analysis. And so when I started as a master thesis student, my task was somehow to make this analysis a little bit more automatic. So because if you look at this picture, so searching for performance problems in an event trace is a needles in the haystack problem. There's a very low abstraction level, and so it was actually Bernd's idea because he defined my master thesis topic. The task was to develop programmatic access to event traces and then automate the analysis. So as you can see here, you can of course zoom into this picture, but still, so there are so many places you might see something here, but you can't really see how relevant this is for the overall execution and how frequent such events occur. So even the level of detail does not really gives you insight, but only at a very specific spot in your execution. All right. Okay. So this was my first project. It was an API to access and analyze event traces. It was called EARL, Event Analysis and Recognition Language. It was first implemented as a Tcl extension. Then later I ported it to Python. We also, I think, had Perl interfaces. So we were always trying to make it usable to as many people as possible. And then you were able to specify so-called patterns in the scripting language that describe certain performance. We call them performance properties in APART. And so what EARL provided was efficient random access to events to various formats. So Vampire was only one of them. There was rlog, cliog. I think these were the upshot and upshot trace formats. And those events, those format-specific events were then mapped to the EARL event trace model. And so the abstractions that EARL provided allow to design very powerful analysis scripts. Okay, so here is the EARL event model. Basically, an event trace was modeled as a sequence of events. We had event types, enter, exit, send, receive, all those had different attributes. I should not go too much into the details here. I think the nice thing about Earl were actually these abstractions, so that the events had pointers pointing to related events. For example, from an exit event, you had a pointer pointing to the corresponding enter event, and from the receive event to the corresponding to the matching send event. And then you could also, it maintained a shadow stack. You could access the stack and also examine the message queue at any point in time. And yeah, Bernd showed already this example. This is the typical late sender example. And here you can see the different events in our event model. And then here are these pointers that allow you to go from, let's say, for example, a receive event to the corresponding enter event, or from a receive event to the matching send event. And again, from the send event to the matching enter event. And then this allowed you to specify these inefficiency patterns in a little script, which is shown here. So it just covers one slide, and it essentially checks or identifies the situation, late sender, computes the waiting time, and then accumulates it in a variable. All right, so as you can see, I'm still showing these slides in the old slide style. So these are logos long gone, probably. More than 20 years old. Okay, then, based on that Earl interface, I designed a tool called Expert, the extensible performance tool. And this was basically a performance tool on top of this Earl interface, and it had a very simple graphical user interface where you could select different performance properties and functions of interest that you wanted to measure. There was an analysis component. This was essentially where you walked through the trace file and invoked different patterns that you selected. Here in your graphical user interface, there was a pattern library which could be extended using plugins, and then again here this Earl interface at the very bottom. The abstraction layer over the event trace. So here's the very first graphical user interface. It was very simple. I think we're very proud that actually at this point there was a graphical user interface at all. Yeah, and we analyzed this interesting code, the Chochalski crystal growth code. It was actually really a nice code. So it simulated the growth of a crystal in a rotating crucible, and it used some sort of an interesting application topology. So it was a three-dimensional cubical mesh, but which was where the ends were basically connected to form this cylinder, and then there was a two-dimensional spatial decomposition. So the processes, basically the structure was. There was a two-dimensional mapping of the structure onto your grid of processes. And most of the work was done in routine VLO, which calculated the new velocity vectors. I think the application itself is long gone, but I don't know whether it still exists. And we looked at communication costs and late sender, and indeed we found that actually most of or a significant fraction of the time was actually spent communicating, and also a significant part of it was actually this waiting time. And so this was a very simple analysis, very simple tool that demonstrated this idea of patterns and event patterns, compound events that somehow describe a situation of inefficiency. And then we came up with a new graphical user interface, which Bernd introduced in his talk, so I'm not introducing it here again. Only again, as a reminder, here you have a tree of metrics, here you have a call tree, and here you have a system tree. All right, this all evolved into the KOJAK project, and Bernd introduced the logo and the general idea. So KOJAK was basically an umbrella project for a number of components that somehow fit together. And it was started in 1998 at that time called ZAM. Today it's called Jülich Supercomputing Center. And I think Bernd and Michael, you were the fathers of this project. And I was I think, the first student to work on it. And there's also a manifesto. I think this was actually here only published in local proceedings. It was later in official proceedings published at the Euromicro workshop. So if you're looking for this, then look for a Euromicro workshop. The first component was this URL, and then we had this analysis tool expert, and later we looked in, when OpenMP came up, we looked into OpenMP instrumentation. I think this was mostly Bernd's baby, the POMP instrumentation interface for OpenMP. We had a first prototype of our own tracing library, which was called Epilogue. For some reason, we couldn't use the Vampire library because it was commercialized also, so we had to develop our own. And later, Vampire actually came back to us to get our tracing library. And yeah, we had a first prototype of the KOJAK GUI, which you have seen. And 2003, I moved to the University of Tennessee, and then it became a collaborative project between Research Center Jülich and the University of Tennessee. We had a new logo with the colors of Jülich and Tennessee. So the Tennessee is the volunteer color, the volunteer orange. And 2004, we had our first release 1.0, the new GUI component Cube, which Bernd introduced, six diploma theses, already 1 PhD thesis, 22 publications, and so forth. So it really took off at this time. All right, then basically we introduced this new high-level picture. So the idea was always to start from a huge amount of low-level performance data, in this case trace data, reduces to something more compact, something more high-level, and map it into this structure. So problem, call tree, system, location. This is the structure underlying also our graphical user interface. Yeah, and the basic workflow is you go through the trace, search for these patterns, calculate a high-level call path profile, which is then displayed here and has all these nice metrics: late sender, late receiver, late sender, wrong order, late broadcast, and so forth. Yeah. All right. In most cases, these performance problems describe wait states, but we had by around 2004 already a significantly large tree of performance properties, inefficiency patterns, which are all shown here. So there's the MPI branch, and then there was an OpenMP branch. And so this was all already quite elaborate. All right, then a few new extensions came up. So one idea was the cube performance algebra. So the idea was to take two profiles and then you combine them using some operator. So for example, you calculate the difference. Yeah, and then you get something that tells you the difference between two executions. And here's how this was displayed. So in the graphical user interface, we had this sunken and raised reliefs. Sunken reliefs showed negative values. Raised reliefs showed positive values. And this was, so when you calculate a difference, you can see basically performance improvements, which is the raised relief, and performance degradation. This is the sunken relief. So you can see where things got worse and where things got better. Yeah, and so if you, for example, remove certain weighting, if you, in this case, a barrier was removed, and with this barrier, a significant amount of waiting time, but that waiting time showed up somewhere else in the program. I think overall we made some gain, but the waiting time didn't disappear altogether. All right, then we looked into virtual topologies. Here's this famous Sweep 3D benchmark, which calculates some Newton transport problem, and it uses a wavefront algorithm. So data is propagated through a two-dimensional grid of processes, so along this diagonal line. And this is basically from Sweep 3D, and when you look at it in Vampire, you only see these. You see this racked profile of communication time, which doesn't really make a lot of sense. But if you actually map this onto the virtual application topology and then sort waiting time or break down waiting time by the direction of this wavefront. So it goes from one corner to the opposite corner and then from the next corner to the opposite corner. So it changes direction all the time. And if you sort that out, then you can actually see that the waiting time shows up at the opposite side at the opposite side of the wavefront direction. So the wavefront goes from here till here. And these processes, basically, they have to wait for the wavefront to show up here. And this is where this waiting time here appears. And this is how you can interpret, basically, this pattern here. All right. This was then now, I think, already the, let's say, final state of the KOJAK project. So we had the automatic multi-level instrumentation execution on the parallel machine. Then a number of local trace files was generated. Those trace files were merged. And there was some definition files, so IDs for regions or other entities. And then here the trace file was analyzed and we got these global results. And so the reason why these boxes are shown in red is because we're scaling bottlenecks. Yeah, so here you have basically trace files that scale with the number of ranks that you use. And here you have a single-threaded analysis. Sorry, here you have a single-threaded merge component and a single-threaded analysis component. And so the bigger the trace files got, the more those, so the longer these steps took. And we discovered that this is not going to carry us far beyond 1,000 ranks. But Moore's law actually forced us to go beyond that. And so we got a little bit frustrated with event traces. So when traces were becoming too wide, they were too long. The frequency of the events, if you didn't do the instrumentation right, was too high. And trace files simply became too big for our tool chain. And the next idea was then to parallelize the analysis. And so now the analyzer is shown in green because it's a parallel program in its own right. It uses, again, another abstraction layer, which is called Parallel Event Analysis and Recognition Language. And still, so in reality, there were still some bottlenecks in that tool chain. So you had all these definition files which introduced numeric identifiers for source code entities, regions, and so forth, ranks. And they had to be unified, which took some time. And then, the local analysis results still had to be combined. So these were actually two bottlenecks we have been working on for several years. I think finally, actually, we managed to do it in a scalable way, but again, it took us a couple of years to get there. All right, so this idea of analyzing traces in parallel, this was the foundation of the Scalasca project, and Scalasca was the successor project of KOJAK. It became soon a joint project of Research Center Jülich and the German Research School for Simulation Sciences, which was a joint institute of Research Center Jülich and the RWTH Aachen University. And the idea was essentially to provide a combined profiling and trace analysis tool that supported the, let's say, most popular programming models, in that case, MPI 1 and 2, and basic features of OpenMP. It became also open source. And so at 2010, the Scalasca team was already actually quite large. So it was basically the union of Bernd's team and my team. And so as you can see, we were at the heydays of Scalasca. We were 12, 13, 14, 16, 17, 18 people. And Brian was also part of that team, and he worked also on a number of things, including, so maybe Brian, you will tell later in your presentation, So he worked on profiling components, but also did these large-scale trace analysis of sweep 3 that I will show in the next moment. All right, this was then basically the final picture of Scalasca. So it's basically the same tool chain as before, only, let's say, with bottlenecks removed. So here we have a measurement library. You can generate normal profiles. Then here you can turn traces into high-level profiles. We call that weight state report, and then analyze it. Here we have this extended graphical user interface going away from a tree structure to the topological structure. And so here this graph shows the scalability of the trace analysis. And was actually the parallel trace analysis was really quite scalable. And this was because it essentially replayed the traces. So if you were able to generate the traces at scale, then we're also basically by definition, by design, able to analyze them in parallel. So this is the uninstrumented application execution on Eugene. This was a blue gene P system, right, Eugene? Joaquin was the...
Eugene was P.
P, yes, P. And then we had the parallel trace replay, basically, was aligned parallel to the uninstrumented execution. But as you can see, so that this is just the trace replay. There were still a few steps, this whole unification and all these auxiliary steps that kind of still showed up as some, let's say, not ideal scaling behavior at least. All right, this was an analysis that Brian has done. It shows the Sweep 3D virtual process topology. And so once we saw this picture, we were actually quite astonished because we didn't really understand where these, and I think we still don't understand where all these lines come from. So apparently, some hypothesis we had, but which is still unproven, is that these are actually because it's a wavefront algorithm, that what we are seeing here are actually optical effects. Yeah, so this is kind of a lens here in the middle, some domain where the wavefront propagates at a slower or faster speed. Yeah, and probably slower speed, I think, and these are refraction patterns. But this is a hypothesis that we always wanted to further investigate, but I think didn't have the time. Oh, it's a bug in our tool chain, right? Yeah. Okay, this is also a work where I think Brian actually took the lead in. This was where we used Scalasca to improve the performance of the computational fluid dynamics code from Aachen. It simulated a blood pump. So this is the ventricular assist device. So something that helps the human heart, the weak human heart, to pump the blood through the body. And so here, what you see here in this diagram is time steps per hour. So basically, higher is better. And as you can see, the original version didn't really scale very well. So the performance dropped down as you scaled beyond 1,000 processes. And so with the improved version, we were able actually to still see significant performance gains, roughly proportional to the number of resources that we used. All right. Yeah, the next big thing in Scalasca was the delay analysis. And this was the PhD thesis of David Böhme, who works now in Livermore, which was my, I think, third PhD student. And so here the distinction is basically this work distinguishes between direct and indirect waiting time. So the idea is that waiting time actually propagates through the system, that delays in one place cause further delays in other places. I think the best example where you can experience this every day is the German railway network. Yeah. And because it's so overloaded, yeah, so it's quite easy for waiting time to propagate through the entire country. And even to some degree beyond borders. And so it's essentially, the work was essentially a scalable version of some prior work by Mayra Jr. et al. And the analysis here attributes basically the cost of wait states to delay intervals. So the idea was, so here's actually the initial delay happens here. Here's the load imbalance, the initial delay here. And that delay causes direct waiting time and later indirect waiting time. The idea was to trace that back to the root cause. And we sometimes call that also root cause analysis. And the major idea was, so previously our trace replay was a forward replay. And now simply we did a backward replay. And with this backward replay, the effects of delays propagated back to their root causes. This was the essential idea. And yeah, so here you can see a little example. So this is sysmp, is I think a code that simulates something detonates a blast or something. I think it's in some astrophysical, some astronomic scale blast somewhere in the universe. And here you can see the computation. So here you can see basically the blast and what belongs to the blast and what doesn't belong to the blast. Then here you see waiting time, which is kind of clear because where people are not, ranks are not working, they are waiting. And you can see that basically the delay cost on a in the spatial dimension, they are basically caused by the boundary between the, let's say, high load regions and the low load regions. Yeah, here's another example where we actually use this analysis to optimize a physics code. So the physics code also has some, let's say, computation in the center of the virtual application topology. But the code was basically full of wait states, propagating wait states. And here you can see the original version, everything red. Here's the optimized version, basically only the, this part still red, and here the costs of the direct delay in the optimized code are also significantly reduced. Okay, here's a similar example where we analyzed the sea ice component of the Community Earth System model. This was a collaboration with the National Center for Atmospheric Research, and so essentially also here sea ice is of course what you typically see at the in the polar regions, and in this simulation most of the work needs to be done for polar regions, which means the equatorial regions have to wait. And so direct waiting time basically occurs here at the boundary between the polar and the, let's say, more central regions. And then indirect waiting time shows up basically mostly in the equatorial region. And so we were, this helped us actually a lot to understand what's going on there. I'm not sure whether we were able really to solve the problem in the end. It's somehow a problem that is kind of in the design was in the design of the code, but we were at least able to better understand it. And maybe
we're fixing it right now. We're getting rid of the Earth's ice.
Yeah, that's right. Yes. Okay. Yeah. So this is out of the box thinking. All right. Okay. So around 2007, the Virtual Institute High Productivity Supercomputing was formed. Bernd mentioned it already. We have, it's an initiative of HPC programming tool builders across the world. So we started with 4 partners. We are now 14 partners, and I think there are 2 more currently applying for membership. So it's only growing. It's also, I think, that it still exists. One of the reasons is that it's a very lightweight organization. It's not even a legal entity. Just we have some bylaws, but if you want to join it, you don't have to sign any contract. You don't need to get in touch. So if you get in touch with your legal department, it's your own fault. And so the mission components were tool development and integration, training, and I think training right now is still the most important component, support, academic workshops. So we co-organize the Pro Tools workshop series at Supercomputing. And maybe one of the things about tool development and integration, and here I was actually hoping that Bernd would show a slide, which he did not. So tool integration in the early days meant tons of conversion tools to convert from one performance data format into another performance data. Yeah, and so we had a picture we were very proud of, I think, where we were able to basically convert everything into everything and make everything work together. But at some point we realized that maybe conversion is kind of a waste of time and that it's better to just define common performance data format, which we did in the SCORP project later on. So the time of the conversion tools is over.
Felix,
yeah.
Just a quick definition on productivity.
Yeah, productivity, quick definition on productivity. So productivity means that we are not only focusing, our focus was not so much to, let's say, make the, not only to make the computation faster, but also to make the development faster by giving developers easy to use tools, yeah, which is hard enough, yeah, easy to, yeah. Tools that actually work and that are easy to use. And even though you can maybe still complain about one or the other tool, I think we made some progress in that direction. Yeah. All right. So this is basically the SCORP measurement system that introduced that new era of joint performance data format as opposed to conversions at every step, yeah, and so it was essentially designed for, initially designed for 4 performance tools: Vampire, Scalasca, Tau, Periscope. Periscope, Michael, was your tool. It was the only tool that used this online interface, so all others were offline tools. And well, this was a multi-year effort. It was actually supposed to emerged from the Virtual Institute funding, but it, like most public projects, I think the total cost was 3 times higher than what we initially times pi, yes, yeah, it was higher than we estimated in the beginning, but eventually we succeeded because the BMBF was very generous, so they funded one project after the other to allow us to complete this work. And yeah, I mean, they could still fund some maintenance work on this, hopefully. They do actually in the Euro HPC program, so I don't want to be unfair. All right.
Can you go one more slide? Because we talked about productivity. Now, next question, which of these 4 tools do you consider is or was easy to use? Honest answer.
Honest.
So we have one of these tools we had experienced twice, and that was absolutely not easy.
Yeah.
I'm thankful that none of the reason.
Yeah. So Bernd showed in the morning in his presentation that our Japanese colleague was at least able to use Scalasca without our help. So he was an experienced guy, probably not a novice user, but still he managed. So there is some evidence that Scalasca is not totally difficult to use. And I think Vampire is also easy to use, but it's hard to find performance problems in the trace visualization. And yeah, well, I mean, the others, so Tau is used all over the HPC landscape, and Periscope, I'm not sure whether it's still, does it still? It's okay. So it was easy to use. It was easy to use. Yeah.
But which of these tools had the largest number of external users?
That's hard to say. I'm not sure whether we can really tell. So I would say these 3, they all had installations across the globe. And because it's also not so easy to, because they were all using this common measurement infrastructure, it's not so easy to differentiate between the different tools.
I mean, I don't want to criticize it, but as you say, it's really hard
yeah.
to prepare such a tool that kind of is easy to use by outsiders.
Yeah.
So we tried out twice with really good students, and just was unbelievable.
Yeah. Well, so I think they're easier to use than they were in the past. So can we agree on that? Can we agree on that statement?
But this is a pretty global problem. I spent a lot of time working with Jesus Labarca, has these amazing tools, but every tool requires Jesus Labarca to come with it, so you can figure out how to use it.
Yeah.
And
Even in the DSC.
even the DSC.
Yeah.
They just get the things and put on his desk and say, okay, tell me what's happening.
Yeah. Well, okay. So now this. So at least in my own career, this is now kind of an inflection point, because I was mostly working on tracing tools, and somehow I thought that so now we have analyzed traces automatically. We have analyzed them in parallel. We made some progress, but maybe there's something else that could be done. And then I started actually working on performance modeling. So here, the starting point here is basically the observation that if you have your application running on your cluster, it does a decent amount of computation, communication is already quite significant, and then your university buys a new cluster, a bigger cluster, and you want to run it on that system. And so then once you execute it the first time on that system, you experience this. Yeah. So, and this is something that you want to basically, this is a negative surprise. It makes the big system unusable for you, and you need probably several months to recover. And the idea was to prepare people for this before the situation actually occurs, so that there's still time to fix it. And the main instrument for this is a performance model. I had always deep respect for performance models. I read these papers by Adolfo Heusi and colleagues, and so it was kind of seemed to me so difficult to actually come up with a formula that tells you execution time is a function of different execution parameters. And so this is basically in the simple way a performance model that shows the execution time as a function of the number of processes. So the example that you can see here is clearly a scaling bottleneck, because the time to compute should actually shrink as you increase the number of processes. It should not grow, or at least it should remain constant if you do a weak scaling experiment. So this is clearly a performance bottleneck. And so the practice was actually in the papers that we studied that people would look at these giant codes, and then they would identify kernels of which they thought they would dominate performance at scale. And then they took these kernels and in a very laborious process came up with formulae, leveraging knowledge of algorithms that describe the performance behavior. And the problem was actually to identify these kernels. In principle, you already need the performance model, because should you know which part of your code dominates performance at scale if you don't have such a model? So then this basically shows the limitation of the analytical process, and we came up with an empirical process. So we took performance measurements with different execution parameters, so typically varying a mixture of problem size and number of processors, and then using some machine learning to come to learn that formula from the data. So this is the simple idea. And well, instead of modeling execution time, you can also model other things like floating point operations, data volumes. Yeah, so there are various applications of or variants of performance models with different applications. And there's a few challenges. So first of all, when you make performance measurements, you experience run-to-run variation. Yeah, so performance is never really the same. And the second is that simply depending on the number of parameters your model has, you need to conduct really many performance experiments, which actually are quite costly. So how to deal with noisy data? So our very first approach was actually to introduce a prior into the learning process. A prior in machine learning terminology is an assumption about the probability distribution that generates the data. And our idea was that actually time is roughly proportional to effort, and effort can be counted. Yeah, so it's computation, memory access, communication, I/O, and the effort is somehow something that you would also find in an algorithm textbook. Yeah, and we came up with this performance model normal form, which shows essentially restricts the search space to formulae that you would also find in a performance in an algorithms textbook, some polynomial expressions with logarithms. Yeah, and the basic idea is you select parameters. So, for example, number of processes, problem size. Then you configure your search space. So you define which exponents you allow here and which you don't. Then you do linear regression, cross-validation, finally some quality assurance. So calculate some fit metrics. 1 second. And then you know at least which models fit the data well, which models do not. And this whole thing is also available for more than one model parameter. Then it looks a little bit more complicated, but it's essentially the same. Yes, please.
Right. So a lot of the machine learning, at least from the presentation, it seems like you're working on the assumption that the computation is not data dependent. For example, if I'm simulating a material that has a lot more cracks and fissures and things like that, then that would take more time. So it seems that's not how correct.
Yeah. So let's say in most of our examples, we assume that the performance depends on the problem size, but not on, let's say, very application-specific problem characteristics. This is something that you then need to express in new model parameters. Yeah. Yeah, that's correct.
Another related, in a way, when talking about noise, you mentioned data noise, didn't you?
I mentioned performance measurement, so system noise that makes your...
Because there was quite a lot of interesting work in the area of operating system kernel noise.
Right, yeah, that kernel noise,
When you scale the number of nodes, and then suddenly one of them is basically...
Yeah, so we studied that work, and so some progress has been made, but there's still run-to-run variation. It's not only coming from operating system kernels, it's also coming from the network, from the file system.
No, they fixed the operating system noise issue as far as I know. That was 20 years ago.
Yeah, they did that on the Blue Gene systems, but the more recent systems are not so noise-free. Yeah.
It will be Linux, whatever, kernel.
Yeah. Correct. So while we were using Blue Gene systems, we didn't think about noise. So those systems were really almost noise-free. Yeah. Also because the applications ran in quite isolated partitions, the way the network was designed. But today you have, for example, these Dragonfly networks, and they're by design shift somehow the network capacity around between applications, and so applications with high communication demands interfere with applications with low communication demands, and so forth. Yeah, so there's still some noise still exists, and it exists for a reason, essentially to load balance. Yeah. Okay. Well, this is then the new graphical user interface. So I guess you somehow remember the picture. It's the Cube performance profile browser, just showing here performance models instead of values, and then showing here, visualizing here the models in this middle pane. Okay, then we thought about how can we reduce the cost of the performance experiment. So when you have two parameters, so our first idea was take basically 5 times 5 measurements and then repeat every measurement 5 times to account for noise. And we found that this is too costly, so we thought maybe we can do better. let's just do one row in this direction, one row in this direction, and then select a few more points to somehow establish the connection between the two parameters. And so our first idea was, so basically we didn't have a first idea. And whenever computer scientists don't have an idea, they resort to artificial intelligence. And so we created a reinforcement learning environment where we use synthetic performance data and let some agent pick experiments and come up with a strategy. And from that agent, we derived a strategy which was take always the cheapest points first. Yeah, and we tested that in different case studies here with different applications. And here's the number of extra points. Here's the prediction error for the, let's say, top right point. And here are the cost savings as opposed to a full matrix. And as you can see, that strategy works actually quite well. But we didn't believe our agent, and we thought maybe instead of taking here all these cheap points, maybe it would be better to pick one more expensive point. And we are currently working on Gaussian process regression as a way to choose these points. And so Gaussian process regression basically identifies the points with the biggest uncertainty. And if you choose those points, they give you most of the value. And then, of course, you need to trade off cost versus value. And this is what we are currently doing. And so the results are also promising, but I'm not showing them today. Okay, here's another interesting work maybe that we did with Thorsten Höfler's group. It was actually a main author was Martin Zoppik, PhD student of Thorsten. And another way to reduce the cost of the experiments is actually to narrow the number of parameters. And to select the parameters, you need to understand which parameters actually influence performance. And the idea here was to use taint analysis. So taint analysis is actually a technique from computer security. So you basically trace the flow of data through your program. So this is why it's called taint. Yeah, it's like you taint the input parameters, and then you can observe how they propagate through your program. And with this, we were actually able to, in experiments, narrow down the number of parameters to reasonable parameters and also improve the instrumentation. So when you know that a parameter does not influence a function's performance, you don't need to instrument that function. And then you can make your experiments cheaper, reduce the overhead, and so forth. All right, here's an application of extra P in one of our own use cases. It's a brain simulation code that we developed ourselves. It's a code that simulates structural plasticity in the brain, so how neurons connect to each other. Yeah, and so as you know, the neural network in your brain is not hardwired. So depending on the stimuli that you receive, new synapses are formed, or if you're not stimulated, some synapses might go away, or if you drink something, they might go away. Yeah, and so we, maybe 10 years ago, we met a neuroscientist who was interested in that problem, but he couldn't compute that in a scalable way because he had to compute connection probabilities between all pairs of neurons. And then I thought, well, we have heard that before. So calculating interactions between pairs of objects, this is a problem well known in astrophysics, and there are methods available. And so we thought about the Barnes-Hutt method, and we're actually able to reduce that to reduce the complexity to what we thought was actually n log square n. And n log square n, so the rational here, what you can, so typically the data structure in this algorithm is an octree. It's shown here as a quad tree in 2 dimensions to make it a little bit easier. So basically the, your space is always subdivided in 8 sections, so only 4 shown here for simplicity. And then you calculate the interaction with, let's say, a remote area as a group, and only if that interaction becomes relevant, you break this further down, and then you go down this tree. And so what we thought initially was, so we have to basically calculate, so Barnes hut is n log n. So we have to do n log n in every step. And then for every, as we go down, for every basically tree level, we have to do it again. And the depth of the tree is again log n. So we thought it was n log square n. But that was actually wrong because, so the, in every step, basically, we have to look at only a finite number of sections. So let me maybe first, before we go to that, explain something else. So actually, this work made it on TV. So there's a TV spot if you're interested in it. And so here we used extra p to validate the scaling behavior. And extra p essentially didn't really reproduce this log square. It always said log, and then we thought, okay, log square, log, who cares? Yeah, maybe it's just noise or something. So we thought extra p maybe was a little bit wrong. But then a new PhD student came, and he actually found out that that subsequent, depending on an acceptance criterion theta, subsequent steps have constant complexity. And so for practical scenarios, you could prove that for practical scenarios, it was actually not n log square n, was n log n. So he later theoretically validated the extra piece hypothesis that it was n log n and not n log square n. All right, okay, I'm almost at the end of my presentation. So I said I moved away from traces to work on performance models. For performance models, we only need profiles, and that helped us a lot. So profiles are easy, it's well understood. There are good measurement tools available. And so I would claim that extra P is actually quite easy to use because it does not require performance data at such grand scales. So, but just recently we actually returned to traces, and returned to traces in an area where traces actually scale quite well, and that is I/O. Yeah, so one member of my group, Ahmad Taraf, he is working on analyzing the frequency of I/O phases. And this is a collaboration with people from INRIA in France. They have developed a I/O scheduling algorithm they call iSet10, which basically groups applications by their I/O frequency, and then applications with the same frequency, they have only mutually exclusive access to the file system. That's the basic idea. And to make it work, you need to find the frequency of the I/O fast. Yeah, you need to do it online. And FTIO is just such a tool that does it online. It can also do it offline, but so it applies essentially discrete Fourier transformation and identifies the period of your I/O and also identifies the confidence. Yeah, so how well it thinks how periodic the application actually is. And with this, we were actually able to make this I/O sets scheduling method work. So here you can see our results. So this is the stretch. This is the slowdown of test applications compared to running in isolation. And so if you do nothing, then the slowdown is actually quite significant. If you apply I/O set in a clairvoyant version, that means with basically the ideal periods are hard-coded, so you just feed it with the actual periods that you somehow measure elsewhere. Then you get down here, and with FTIO you get very close to that. So here we have the stretch of 1.1 in an ideal scenario and a little bit above 1.1 with FTIO. So here is FTIO with some artificial error. So you can see that actually our so here we are saying basically it could be worse if it wasn't that accurate. Yeah, it could be worse. So we're actually quite close to the optimal, and our predictions are also quite quite accurate. Here's the same just with utilization, so the fraction of system time spent on computation. Here is basically the ideal situation. This is with FTIO. This is with FTIO plus some artificial noise, and this is the original version. So, so with FTIO, we have a tool that is also lightweight, that scales, and that has some impact. All right, so with that, I conclude my talk. So it was basically tracing from 25 years back until today. Here are a couple of papers. It's not an exhaustive list. So just the main papers of about these different tools. And here's also a non-exhaustive list of people I would like to thank who contributed to this. So yeah, here in this room, I would like to especially thank, of course, Bernd, who was my supervisor for my master thesis and for my PhD thesis. Michael, you initiated this project, and Brian, we worked together for many years on Scalasca, and made it actually work at this scale. And Martin, we also worked together on extra P, at least for shorter periods of time. So yeah, well, thank you very much. Also, thanks to our funding agencies, and well, I'm happy to answer questions.
I would be interested to understand, so your formulas for prediction of performance, did you find that it's application people that know their application by heart, probably, as groups working on the same application since years, they could come up with this also without the help of the tool? Or is it something that they really need to find these formulas that are important to decide whether it scales to larger machines?
So I can show you examples where we actually identified scaling bottlenecks the developers were not aware of. So one of them is, for example, HOM. It's a climate code, and they had some scaling bottleneck in an initialization routine. And so following the, let's say, classic scheme that you would look for these computational kernels first, which you rarely look for in initialization code, they overlooked it. Yeah, but it was actually quite significant. It was easy to fix. Yeah.
Mm. So it's difficult for application people to think in that way, right?
Yeah. So it's. I think this is basically this term algorithm engineering captured it quite well. So they have expectations, but their expectations not always meet reality. Yeah. So there's a gap between how developers think of their code and how it actually performs. And our task is to cast light on that gap. Yeah.
I have a question for both of you. We had the idea of Scalasca parallelized analysis, and in the old system it was one trace track and one analysis core, basically, right? It was a one-to-one match. You don't have this anymore in the current system because most of the parallelisms on the GPU and typically running tools on the GPU. So you plan to redesign this, the goals to redesign this to take advantage of increased node capacities, or is it not necessary?
So the trace analysis, so we are currently not working on expanding the trace analysis towards GPUs. There has been done some work by Wolfgang Nagel. So there was this kubT interface, you remember, which allowed to track at least kernel invocations, data transfers, so the, let's say, high-level operations between GPUs.
Yeah, so we currently thinking about adding new patterns for interaction between the CPU and the GPU or something, but not so much what's happening in the CPU itself. And for that, basically, the idea is it's not so much to analyze so that the NPI process who controls typically a GPU, like in the rerun, that process would analyze the events coming from the GPU and the interaction with go on. There would be a next step to like look at things happening inside the GPU and GPU-specific patterns, and then use the replay on the GPUs to do it. I don't know, but this is going.
Once the MPI starts to infest the GPU, whether we're going to run MPI out of the GPU, which are the plans that we have, then just make it tricky. That's actually
it's a good thing.
So from the code stuff, doing communication.
Yeah.
exactly right.
All right, further questions?
So I wonder, all these tools, one of the important performance bottlenecks is memory access.
Mm-hmm.
So none of the tools actually did something about that, right?
Not entirely true. So in Extra P, actually, we looked at memory accesses in two ways. So first of all, we looked at main memory consumption, which is also a scaling problem. And we also looked at reuse distance. So you remember still maybe the thread spotter tool. So by Eric Hagerston, he had developed a reuse distance sampling technique, so a scalable technique to capture the reuse distance. And we took basically what was left of his tool and measured the reuse distance for different sections of the code. And then we checked whether the reuse distance would actually change with problem size. So for example, whether bigger problems would be less cache efficient. Normally, you would expect that people design their algorithms in some blocked, tiled way where the overall problem size has no influence. And that was actually true in most cases. Only in milk, I think we noticed a slight increase of the reuse distance with increasing problem size. Yeah, but in most cases, there was not really a notable difference. Yeah.
I have one more question. What is kind of striking to me, you're the only performance analysis researcher or performance tool researcher that really substantially talks about the term complexity. And complexity analysis is, of course, also some kind of performance analysis, which is very important. But is there a tool that actually is able to derive a complexity expression out of a very problem?
That's Extra P.
But for what kind of problems?
So for all applications. Yeah.
OpenMP, MPI, you can...
So we can do this. It works best with MPI. With OpenMP, it's a little bit harder because with OpenMP, you at some point hit the memory bandwidth barrier as you increase the number of threads.
With OpenMP, it doesn't work.
It works. So we have done, for example, we have used Extra P to analyze OpenMP itself, how the OpenMP constructs scale, whether they are scalable or not. Yeah, so for example, when you create a team of threads, you would expect that it can create some effort that is proportional to the number of threads, or you do it in a hierarchical fashion where the effort is then logarithmic. Yeah. So I would say it's harder to use with OpenMP, but you can still get useful insights with OpenMP.
And can I also give you a serial program and you give me like a, best case analysis in terms of how much parallelism contains?
Not how much parallelism. So what we can do is if you give me a serial program, we can tell you how the execution time grows with the size of the input problem.
But the input parameter, I have to tell you, you don't know what that is, right?
Yes. Yeah.
What if it's multiple? It could be like n.
Yeah, then you need to create models with multiple parameters, and then the experiments become more costly. So I would say 2 or 3 parameters we can handle. 4 is really hard. Yeah, so we have another tool that we work on. I didn't talk about it today. It's called DiscoPop. That stands for Discovery of Potential Parallelism. That does some static and dynamic data dependence analysis to identify possible parallelization opportunities and also make suggestions on how you can implement them in OpenMP. All right.